Hello and welcome to the second lecture of our new module that we started with the last lecture. And this module is on multiple random variable, and in the last class we discussed about their joint distribution, joint PMF, PDF, and we concluded that last class saying that we will be starting the marginal probability distribution in this class. So before that, we should take first that one example that we didn't do in the last class. So that example will start with today's lecture, which is on that joint PDF, and after that we will start the details of this marginal probability distribution. The example that we are going to discuss, it will also be useful to understand that marginal probability distribution as well, because the same probability distribution is used just to demonstrate that how it is related, that the joint probability distribution and the marginal probability distributions are related to each other. So our today's lecture is on this marginal probability distribution, which we are going to take that outline of today's lecture as follows: that this multiple random variable that we discussed in this last class is a joint probability distribution. So we will discuss the problem on that first, and after that we will come to this marginal probability distribution and its details about the thing. So here one thing, before I go through that problem, I just want to give you the overall concept, and on that concept basis, if that is clear, then means the relation between this that joint PDF and its marginal will be very easier to understand. So if you now see here what we are looking at, this joint and this marginal is like this. So as we have told in the last class, that if suppose that these are the two, so we are now, because whenever I told that whenever the pictorial representation is there, we can go for this bivariate one. So and the concept can be extended to this more than two variables as well. So here what we have seen, that these are the two axes for these two random variable, and depending on whether these random variables are discrete or continuous, we will get whether the probability mass function that is concentrated at a particular point, or this will be a surface kind of is a three-dimensional surface kind of thing that we have seen it earlier, just to give some. So this kind of surface also we can get for the joint distribution. Now, so this is what we can say, that this is when we are saying that this is a joint PDF that we discussed in this last class. Now, where it is related that through this marginal is that I just want to know the variation or the distribution of one random variable that is interest to me. Suppose that I have this joint probability distribution and I want to know what is the distribution over this axis, over this axis means for this random variable x. Now it's like this, that sometimes irrespective of the distribution of the y, I just want to know what is the distribution of y. The joint PDF, what it is showing, that as we discussed in this last lecture also, that this is the behavior of the simultaneous occurrence of both the variables. It is true that but it should not be understood that whenever we are talking about the marginal, it is not at all related to this joint distribution, or it is similar to the single random variable, not like that. So what is that joint PDF is there, I am just interested to know for a particular value of x, irrespective of the distribution of this y, what is the distribution of this x. Now when we are talking about the irrespective of the distribution of the other random variable, that means I am just marginalizing out the other random variable just to get what is the distribution of a single random variable. Now very crudely, which is definitely or the mathematically not true, I repeat before I state what I'm going to say. Mathematically, that is not true, but very crudely, if you just want to visualize it in this way, that suppose that you are taking a source of light parallel to this x, so that for this surface you will be seeing a shadow of that 3D object on this plane, that is y and this fx, that joint probability density. So, the shadow that we will see it here. So, one shadow you will see here. Similarly, if you put the source of light in the parallel to the y this way, then you will see a shadow on this x axis. Now, this shadow is obviously not the marginal distribution, but you can see it in that way, the how it is distributing only with respect to the y alone or with respect to the x alone, that is only for the one distribution. So, that you can say that is the marginal distribution, but obviously mathematically we will see that how this marginal distribution can be obtained from this joint PDF. That we will see. We will first take up a particular problem where we are discussing about the joint PDF of one joint PDF problem from so that the problem we didn't cover in the last class. So, after that we will take up the same problem, same joint distribution to find out their marginals, so that we will just see how they are related. So, this will be, so taking the reason for taking up the same problem is that we will be seeing that whether how these two things, the joint PDF and the marginals, are related to each other in a mathematical sense. So, we are starting with that problem first, as I am telling. That problem is states like this, that a storm event occurring at a point in a space is characterized by two variables, namely the duration of the storm and the intensity of the storm. Again I should say here that a particular storm event did not be characterized only by two random variables. There could be some other random variables as well. For example, the total amount of this rainfall is also one variable, that generally we take these three variables together to characterize one particular storm event. But here, as we are discussing the bivariate case, we have taken the two random variables together. So, at this point of time, I just want to tell one thing, that even though we are saying that this concept can be easily extended to that higher number of random variables, that is more than two, which is possible, no doubt, but it may not be mathematically always very easy, and that also we will just discuss in the light of this marginal distribution that we are going to discuss today's lecture. There are some very new concept has come up, say for example, that copula, where we can still the research is going on how to take care more than two random variables to study their simultaneous behavior. So, the concept can be extended easily, but it may not always be mathematically very easy to capture their behavior together. But here obviously we are taking the bivariate case, that is why the two random variable which characterize a storm event, we have taken it in this problem. So, those two random variables are, one is the duration of the storm event, and another one is its intensity of the storm event has been taken care. One is denoted as x and other one is denoted as y. And there are several such such storm events, such storm events are taken, and their duration is obtained separately, and from the duration it is found out that it is following a cumulative distribution of this 1 minus e power minus x, which you know that this is an exponential distribution. This is a cumulative distribution from the exponential with the lambda value is equals to 1 here. And also that rainfall intensity is also analyzed and seen that which distribution it is following, and that we have found that this is also an exponential distribution with the lambda value is equals to 2, and its cumulative distribution is 1 minus e power minus 2y. Both this x and y are greater than 0. Now the question is, from the joint CDF of this x and y is assumed to follow an exponential bivariate distribution given by this this distribution. So their joint distribution is like this, that 1 minus e power minus x and minus e power minus 2y plus e power minus x minus 2y minus cxy. Now thing is that here lot of question can be raised, that how we know that this is the joint distribution and how we can say that those are the marginal distribution. Those discussion will come up in a minute after this problem while we are discussing the marginal distribution. But here what is our focus of this problem is that those are those separately has been seen that is following an exponential distribution, and this joint distribution, if it follows like this, it is assumed, that's why it is very clearly stated, if it is assumed that joint distribution of this x and y is following this one, here the question here is that is on the parameter c, which is shown here, that c. Now what is the possible this range of this c, that c denoting a parameter describing the joint variability of the two variates. So how these two variates, as x and y, the duration and the intensity, how they are varying together, what is their association to each other. Obviously this is mostly the linear association that we are talking about. This will be more clear when we will be in the module 7, in the last module, when we are discussing about this that correlation or the covariance, then it will be clear. But here you can just see that c is a kind of parameter which is describing the joint variability of the two variates. Here so here our question is very simple, in the sense we will just find out the possible values of the c that it can take for this distribution using the different properties of a joint PDF that we have discussed in the last class. So to know the possible values of c, we have to find out the lower and the upper boundary of the c. To find out the lower bound of the c, we know that all bivariate distribution, that is this fxy and this fx is less than equals to this fx. Now this, when we are talking about that, this is a property that this density will be less than equals to this one. So this is a property when we will discuss in terms of this marginal probability distribution. So in this context, just I can once again take you to this pad that I just wrote it here that few moments back, that I was just talking about, that if you just put a light in this location, and the shadow of this one can be crudely assumed to be the marginal distribution of this joint distribution over this axis. Now if you just little bit we can extend our imagination, that instead of just throwing the light and light is just producing a shadow, instead of that, if we just assume that when this light is going here and this a particular value of this y, if we just, this is whatever the ordinate that we are getting here is nothing but the summation of this line, sorry, this line is parallel to the x axis. So this light is coming through this one, when it is penetrating through this joint PDF surface. Now whatever the ordinate that it is getting, it is going on adding them, and at the end in terms of its shadow, it is just producing one ordinate which is the summation of all the ordinates that it comes. So I am just putting the same concept here, it is the producing one shadow, but instead of this shadow, you know that from the physical thing, it will be the maximum height, wherever it is getting, it will just produce that one. Instead of that, I am just asking you to extend your imagination, that when the light is passing through, it is going on adding the ordinates and producing the sum of this one. If you can assume this one, then this is perfectly the marginal distribution in terms of the mathematical description as well that we are going to discuss now. So what is now here is important is that now you can see that the marginal is obviously the greater than the what is their joint PDF. So that is what the that property is being used here, that this joint PDF is for the any of this x and y should be less than equal to its marginal. So using this property, what we can do is that because the joint probability cannot exceed the probability of this probability x less than x. So this is also can be clear, that is so as we are taking this marginal, that is a concept just now I have told. So using that one, it is easy to understand that the joint probability, that is the probability of joint occurrence x less than equals to x and y less than equals to y, cannot exceed the probability of x less than equals to x irrespective of what is the distribution of the y, obviously is independently of the value taken by the y. That means irrespective of what is the value taken by y. Now if this is the condition we use, then it comes that we have seen both the things. This is the joint distribution and this is its marginal, that is fxx. Now following this inequality, we can directly say that from this one, and since x and y are always non-negative, the inequality holds if and only if that 1 plus cy is greater than equal to 0. So now if we want to know what is the upper boundary of this C, then we have to determine it from the joint, we have to determine its joint PDF. And you know that joint PDF, in the last lecture we have defined that this PDF is the double integration with respect to x and y of this cumulative distribution function. So if we just take this joint distribution of this, if we take the first derivative, it yields that e power minus x minus 1 plus cy e power minus x minus twice y minus cxy. Now from this one, if we take one more differentiation with respect to y, then it comes that 1 plus cy multiplied by 2 plus cx minus c e power minus x minus 2y minus cx, and obviously the x and y is greater than equal to 0. Now this is that this is the joint PDF that we got for this random variable x and y. Now the thing is that another property that we have seen, that for all possible values of x and y, this should be non-negative. So this should be greater than equal to 0. Now you can see that it will be having the minimum value at so at x equals to 0 and y equals to 0 at the origin, we will check that what is its value, and from there we will get that its upper limit, that is for x equals to y equals to 0, that is the joint PDF at the origin is given by 2 minus c. So now this, because this PDF is the non-negative function, we know the inequality 2 minus c greater than equals to 0 must hold. Hence the upper bound of this parameter c is less than equals to 2. So with this one, what we got the possible values that is c can take. Now we will take again this problem later, where we will be discussing that from the joint PDF using that concept of this marginal, whether we are getting to that one. Now we will start that marginal probability distribution, which just what we have discussed now. We will just see how we can obtain it from the joint PDF or PMF, as the case may be, whether it is continuous or discrete random variable. So marginal distribution of a single or the subset in general, I will just come to this subset what I just mean. So for the time being, you can just read that the marginal distribution of a single random variable is its probability distribution irrespective of the distribution of the other random variable considered in the multiple random variable. Now if you see this one, this will be very easily you can imagine it for the bivariate case, which I have shown in this pictorial diagram as well. But this is not only that, this is not only for a single random variable. For example, suppose that there are more than two, if the case is more than two random variables are there, three random variables are there. So say that x, y, z, and we are interested to know that what is the distribution of the x, y irrespective of the distribution of z. Then also we can say that this is a marginal distribution, marginal joint, that marginal distribution of x and y irrespective of the value of z. So that is why, to make the statement general, the word subset is used here. So out of the n random variable, you can just make the subset with respect to a single random variable, or more than one but less than the total number of random variable that is there in that multiple random vector. Now this marginal distribution of the interested variable, that for which variable we are looking for its marginal distribution, is obtained from the joint probability function or the joint PDF. When the effect of the other variables are marginalized out. So here again the marginalized out, the word that we are using here, that means that it's that irrespective of the distribution of that particular that other random variable in concern. So now the marginal probability mass function, this is for the discrete random variable. Now if we just separate out the two random variables, one is that discrete, another is the continuous. So if we just take this discrete case first, then what happens again, if we just take that the last lecture example to start with, that we are throwing the two dice, and the outcome of the two dice, that is consist of the two outcome, and we can say that. So you know that last class also we told that always the association need not be in such a way that it should be related to each other in some sense. The independence is also one association, so there is independently associated to each other. So you know that for throwing a two fair dice together, so the outcome of one dice is the independent of what is the outcome of the other one. But here, that for the marginal distribution, if we want to know, that means the outcome of a one dice irrespective of the other one, whatever the distribution that we are getting here, it should be it should be the same if we just throw a single dice, because they are independent in the sense that outcome of one dice doesn't have any effect on the outcome of the other dice. So here the marginal distribution, that is for this type of cases where the outcome is having some specific distribution, sorry, the outcome is some specific values only. So that time we are getting the discrete random variable, and that marginal distribution is known as that marginal probability mass function, which we can we will get that direct summation of that values over the other random variable. This is what is explained here. So in case of the discrete random variable, the marginal density, known as the marginal probability mass function, is obtained by summing up the distribution of the other variable. So this we'll see again, because you can recall that in the last lecture we gave one example and we just saw that summation, and what does that summation mean, that we didn't explain properly in this last lecture. So I just told that it will be explained in the next lecture in the context of the marginal distribution. So to describe this fact, that is for the discrete random variable where some only few specific values is the outcome. So there, how we are getting the summation to marginalized out the effect of the other random variable, that we'll discuss, and we'll see that how the other one is how we are getting this through the summation. So if the discrete bivariate random vector, one is x and other one is y, is having the joint PMF Pxy, then the marginal PMF of x and y, these are denoted by Pxx and Pyy, is shown. The how to get this to the marginal from this one is just the summation of the other one. So this one, that Pxx, as I told that this is the marginal distribution of the x. From this Pxy of this joint PMF here, when we are getting, we are summing up for all y. This is important, that when we are getting that marginal distribution of one random variable, we are summing up for the other one. So here it is for the x, the marginal distribution for x, we are summing up the joint PMF for all y. Now similarly for the marginal distribution of y, when we are getting, we should sum up for all x. This will be more clear with respect to the to this example that we are going to discuss after this. So before that, if we just take the cumulative one, so those are the again that you can say that those are the that PDF of that x and y. Now for that x and y, that is the individual random variable for those marginal, if we want to know that what is the cumulative density distribution function, so you can following that same thing that we discussed for the single random variable, that is once you know that what is their that PMF, and then you can just summing up you know that how to get from this distribution to that cumulative probability distribution, you have to just go on summing up. So same thing is done here also, that is when you are taking this cumulative distribution function of x is nothing but the x less than equals to some specific value. Now when we are writing that x less than equals to this small x and we are not writing anything about y, that means that is irrespective of the value of the y. So if we want to get this quantity, then what we have to do is that for the summation when we are doing, that is for all xi which is less than equals to x, and for y this should be for all y. Now we have now also, you can see that for all y, when you are summing up, you are basically getting the marginal distribution of x. Now with that marginal distribution of x, if you just go on summing up to some specific value x, then you are getting its cumulative distribution. Similarly, in case of y also, this is just the just opposite. So when you are taking the cumulative distribution of y, then you are just first of all summing up the PMF for all x, and then then the resulting sum is your the marginal distribution of y, and then you are summing up that marginal distribution to up to a specific value y to get its cumulative distribution. Let us take one example, that the example that we took in the last lecture on the stream flow. There are two stations, nearby stations, and the stream flow at those stations are categorized into different stream flow category, and here the 4 such categories are considered to describe this problem. So the problem once again it states that the stream flow at 2 gauging stations and 2 nearby tributaries are categorized into 4 different states. These states are named as 1, 2, 3 and 4. So for both the sides, these states are there. So these categories are represented by 2 random variables x and y. X and y means for the two tributaries. First one is x and second one is y. And the PMF of stream flow categories x and y are shown in the table on the next slide. So what we have to calculate here now is calculate the marginal probability of x and y, and also calculate what is the probability of x equals to 1. So you recall that with this problem in the last lecture we calculated some probability, that is where the x is greater than x is greater than y. That probability we got from that PMF what was supplied. At here we are looking for from that joint PMF how to get their marginals, that we will discuss in this one, and then from that marginal probability we have to calculate that what is the probability x equals to 1. So the probability x equals to 1 will get the marginal distribution of marginal distribution of x. So this is that PMF, that is these are the different states, that is x equals to 1, x equals to 2, 3, 4, and similarly that y equals to 1, 2, 3 and 4. So this is a 4 by 4 matrix, and each matrix, so the possible outcomes are some combination. So this is, so this 0.31 means that probability of x equals to 1 and y equals to 1 is equals to 0.31. So we discuss while describing that joint PMF that this occurrence should be joint, this occurrence should be simultaneous occurrence. So x equals to 1 and y equals to 1, for this particular case the probability mass which is concentrated for this outcome is 0.31. Similarly, the similar expression can be given for all these cells here. Say for x equals to 4 and y equals to 2, the probability is very less, which is 0.001. Now this 4 by 4 matrix is showing that joint PMF. Now if I want to know what is the marginal probability distribution of either of x or y, then what should we do? So this cell, this last column, what you see is that is the marginal distribution of x. Now when we are talking the marginal distribution of x, that what we are doing here is that what is the probability, the asking here the question that what is the probability that x is equals to 1. Now when we are saying this this question, which is also asked in the problem, is that x equals to 1, that means irrespective of the value of the y. So it can take either, so x can be 1 in the case when y can be 1 or y can be 2 or y can be 3 or y can be 4. So x equals to 1, whenever we are talking the irrespective of the value of y, that means any one can happen. Now so that probability of x equals to 1 is nothing but the summation of 4 events which are x equals to 1 and y equals to 1 plus x equals to 1 and y equals to 2 plus x equals to 1 y equals to 3 plus x equals to 1 y equals to 4. That means these 4 probabilities has to be added up to get the answer what is the probability that x equals to 1. So this is exactly what is done here. Now also you can think about that pictorial representation that we gave, that if we are just putting a source of light on the one side and once the shadow is creating, the shadow is nothing but the summation of all such ordinates. This is exactly is following here. So here this is your, in this table, in this matrix form, this is your x axis, this side is your x axis, this side is your y axis. When you are throwing the light here, it is basically going on adding up and creating the shadow here. So this quantities, so this 0.37 is the probability for x equals to 1. This 0.41 is the probability for x equals to 2. This 0.179 is the probability for x equals to 3, and 0.041 is the probability for x equals to 4. So these 4 is showing you the marginal distribution of x. Similarly, if we want to know the marginal distribution of y, then for marginal distribution of y, that is probability of y equals to 1, then we have to add up again that 4 such events, that is y equals to 1 and either of these 4 such events x equals to 1 or 2. So this should be added up like this to get that the probability of y equals to 1 is equals to 0.377, probability y equals to 2 equals to 0.446, and this y equals to 3 is 0.134, and probability y equals to 4 is equals to 0.050. So what we are getting here is that now if we go back, if we just recall our once again the problem that we stated, that is this is the joint PMF that we started with for the 2 nearby tributaries. Now that joint PMF was there, then what is the implication of this marginal distribution? That implication of the marginal distribution is that now for these 2 tributaries, I don't know what is happening on the other tributaries. I am only interested to know that what is happening in this tributary and how we can describe their probabilities. So if that is the case, then so irrespective of the knowledge of the other tributary, I am only interested in this one. So that is reflected in this marginal distribution. So to complete this problem, again this is explained here. Let the probability represents the event that x equals to 1 for this 4 such event, that is 1 1, 1 2, 1 3 and 1 4, and these probabilities if we add up you will get that probability, that is your point. So these 4 probabilities are added up and to get the answer is your 0.37. Sorry, there is a mistake in typing. So this total probability is equals to 0.37, which is the probability of x equals to 1 as we have seen in the table. Now, if we just extend this one to the continuous random variable, then this continuous random variable, in case of the continuous random variable, you know that, so this will be the integration. Again we have to follow the same concept here also, that is let x and y be the bivariate continuous random variable, then the marginal probability density function of one random variable is obtained by integrating the other variable over its entire range. So this one, this fxx is the marginal distribution of x, and this fxy is the joint PDF of the x and y. So once we want to know what is the marginal distribution of x, then we should integrate integrate it for the other random variable which is y, and this is for the entire range of this of the y. So if we do this one, then what we get is the marginal distribution of x. Similarly, we will get the marginal distribution of y if we do the integration with respect to the x over its entire range. Now, for the cumulative marginal distribution, so once we get that fxx, that is this that PDF, then we can do it again, we can do the integration from minus infinity to some specific value x to get their cumulative probability distribution function. Now here if we see it, that cumulative marginal distribution from the joint distribution, what does it mean? That fx of x is equals to probability of x less than equals to some specific value x and y less than equals to infinity. Y less than equals to infinity means it is covering the entire possible range of this y, and you know that which is nothing but, as it is the entire range, which is nothing but is equals to probability of x less than x. So this in the integral form, it will be the for this entire range of this y from minus infinity to plus infinity, this one should be integrated out for this for y, and you know that this is nothing but the marginal distribution. So this is replaced by this fxx, and the outer integration is from the minus infinity to some specific value of x, which is with respect to the x. So again, so this turns that fxx is the nothing but the from minus infinity to some specific value to get that cumulative marginal distribution of x. Similarly, for the y, it is the integration from minus infinity to some specific value of y, and it is integrating the marginal PDF of y, random variable y. So this way we will get both that marginal PDF and marginal CDF. Now the concept can easily be followed when the joint probabilities are bivariate by applying the theorem to the total probability. So this total probability means when you will be discussing the conditional distribution in mostly in the next lecture. That time this comment will be more clear, that how from the total probability theorem we are getting again these distributions from that joint probabilities, how we get it from there. So before we conclude this one, there are two important things that I want to mention here, that joint distribution determines the marginal distribution. Second, marginals do not determine the joint distribution. This is very important in the sense that if you know how we know, that is our that is another issue, but if we know the joint distribution, joint PDF or joint PMF, from there we can determine what is their marginal distribution. But if we know the marginal distribution, then we cannot determine what is its joint distribution. from the traditionally, that is that what we know. If we just give a simple example, and that is also very important to remember while applying in the different problems in the civil engineering, is that sometimes we use the concept of the joint normal distribution. You know, the normal distribution we have discussed already. Now if we get two random variables and we state that these two random variables are having a joint normal distribution, that means that means we get a three-dimensional bell-shaped curve as their joint distribution. Now, if we can declare that this x and y follow a joint normal distribution, then we can conclude that both of them or their marginals follow a normal distribution. But if we get two different random variables, both of them are following normal distribution, then we cannot say that their joint distribution also will be the joint normal distribution. So one side we can do the conclusion, but other side the reverse is not true. This is very important to remember, and that is basically. Now the question is that if we know the marginals, then how we will know that joint distribution. So that I was just mentioning at the beginning of today's lecture, that there is a new relatively new concept has come on this copula, and that copula theory can be used to find out their joint distribution with the help of this with the knowledge of their marginal distribution. In one of the subsequent lecture, we will cover the introduction to this copula theory for this purpose in the later stage. Now we will take a simple problem to start with, that is, if the joint this will be PDF. If the joint PDF of two random variable x and y is given by this expression, that is fx xy equals to 2 for the range 0 to 1 and this y less than x. So this range you can see here, this is that x is varying from 0 to 1 and y is varying from 0 to that x. So this y is always less than x. So this is a kind of the triangular shape over which the probability is that PDF is defined here. So determine their marginal PDF, and straightforward, if we apply our knowledge, that is from that the integration over this entire range, that is fx. So if we get the if we want to know the marginal distribution of x, that is the integrated over the entire range of y, and which is from 0 to x. So starting from 0, it can take a maximum value up to that x. So this is equals to 2x, and similarly y is equals to over, we have to do the integration with respect to this will be x with respect to the x, and this starts from this y to 1, and if we do this integration, we will get that 2 into 1 minus y. Now little bit some more, so that is the example. So this is the example of the uniform distribution, that is because that is the constant PDF form is the constant, which is equals to 2. But if we take it that PDF is related to some their dependent variable x and y. So two random variable x and y having the joint distribution as follows, that is k x plus y, and the range is the 0 to 2 and y range is from 0 to 4. So if we take this range, and first of all, if we want to know that, find out the value of k. Now whenever you know that this problem we have taken earlier also, means this type of problem, that is to find out k, we have to apply that to be a valid PDF, it has to be equals to the integration over the entire range should be equals to 1. And then once we know that k, then what is the marginal PDF of x and y? That is the question here. So here over the entire range, if we do the integration for this x and y, so this is should be equals to 1, and this integration from this 0 to 4, if we take, then this is k x square by 2 plus y x, which is from this 0 to 2, if we take this one, and this one is, so if we go with this, then we will get this should be equals to 1. So ultimately it is coming that 8k plus 16k is equals to 1. So you obtain that k is equals to 1 by 24. So the PDF is if xy is equals to that your x plus y by 24. So this is the PDF form. Now if we want to know the marginal distribution of x, then we know that we have to integrate it with respect to y, and from the minus infinity to plus infinity, so we are taking over the entire range, which is the 0 to 4. If we take this range, and we will get that one from this 0 to 4 for the y, and we will get the range at x plus 2 by 6, and for the x range is from 0 to 2. Similarly, if we take the marginal distribution for the y, we can follow these steps from this minus infinity to plus infinity, and we can check that from 0 to 2, it comes as this 2 plus y by 12 for the range 0 to 4 for the range of y. So one thing you can see that marginal distribution, when we are calculating this, the variable x is not present there because that is integrated out. So this is only depending on the variable y. Similarly, for the x also, it is only dependent on the variable x. Now we will take again that the problem that we have we started with this lecture is the storm event, where this joint PDF is known to us. The storm event occurring at a point in the space characterized by two variables, namely its duration x and intensity y. And what we have seen there is that if this is the joint distribution form, then what should be its marginal PDF for this x and y. So in the earlier problem, we have shown that this is the marginal, this is the joint, and we are asking for this the possible range of this value of y. So now we know only that joint distribution, and we are interested to know what is their marginal distribution. Again, I repeat that this joint PDF is given here, and we are interested for the marginal one. But we cannot ask the reverse question, that is, if this is the marginal, what should be the joint, until and unless we are using that theory of the copula. That we will discuss later. So here what we know, this is the joint PDF is given to us, and I am interested to know their marginal distribution. So to get the marginal distribution, again, that we have to integrate it from this over the entire range of y, and if we follow these integration steps, then we will see that this fx, that is the marginal distribution of x, is coming to be that e power minus x for the range x is greater than 0. And similarly, for the y, the marginal PDF of the average intensity y, it should be equal to that f y from minus infinity to plus infinity. If we do this integration step, we will get that this marginal distribution of y is equals to 2 e power minus 2y. So these are the intensities. Now from here, if we if we want to know what is their CDF, then we have to integrate it again from the lower extreme to some specific value of this y. For example, if we do it here, that is at 2 e power minus 2y, then you know that this is an exponential distribution, and its CDF will be 1 minus e power 2y, which exactly we just stated at the beginning of this class for that problem. And this is also another exponential distribution, which CDF will be 1 minus e power minus x for this range. So in this class, we have seen that the concept of this marginal probability distribution is discussed in this class, and joint probability distribution we have discussed in earlier. So now if we just think about that, we know the joint distribution and the marginal is discussed. After that, one thing is one more concept is important, that is known as the conditional distribution. The conditional distribution means that I am little, so instead of, in case of the marginal, instead of saying that irrespective of the value of the other, I just want to know if the other variable is given some condition, that is the y is this, what is the distribution of the x. So instead of saying the irrespective of the other variable, I am saying that the other variable is this. So that is the condition. So once that condition is defined, what is the distribution of the other? So this is generally known through this conditional distribution, and which is also obtained from this joint PDF. So this conditional distribution will be discussed in the next class. Thank you.